Hi and welcome to another cardiovascular physiology video tutorial. I'm your host, Dr. James Colhane, and today we're going to be talking about blood pressure regulation. Specifically, what is mean arterial pressure, what are the components of mean arterial pressure, and how is mean arterial pressure regulated. So we got a lot of information. Before you actually watch this video tutorial, I would really encourage you to watch the other video tutorials on the RAS system, on the vascular resistance, and the video tutorial on cardiac output. That will give you the specific information about a number of physiologic systems here that are involved in determining what mean arterial pressure is, so that you can kind of put it together in this video tutorial from a big picture perspective. Let me show you a little bit of my cartoon pictures here, and just to get everybody oriented. Up here we have a blood vessel, the brain, and the sympathetic nervous system. We have a kidney down here, a nephron over here, and then our equation that tells us what the determinants are of mean arterial pressure. Okay. Mean arterial pressure is an average weighted mean that reflects what blood pressure is in the body at any given minute. It's a weighted average because if you take a look at the actual mathematical equation that is used to determine what mean arterial pressure is, okay, we can calculate it using this equation. MAP is equal to 1/3 systolic pressure plus 2/3 times the diastolic pressure. So the diastolic blood pressure in our blood pressure measurement is actually weighted more heavily than the systolic blood pressure in determining what mean arterial pressure is, because your body spends more time in diastole. It's a longer period of time in the cardiac cycle than systole, and so we weight that more heavily. So if you took a standard blood pressure like 120/80, okay, so let's see here. We have 120 divided by 3, that is going to be 40. And then we have 80, so that's 160 divided by 30, which is going to be about 53. We'll just do rough ballpark. And that will give us a mean arterial pressure of 93 millimeters of mercury. So with a blood pressure of 120/80, again, your mean arterial pressure is going to be about 93. This equation up here will not allow you to determine what exactly mean arterial pressure is. It's more of a mathematical relationship, showing you what the major factors are that determine what mean arterial pressure is at any given time. And those two major factors are cardiac output and total peripheral resistance. Now, cardiac output and TPR are actually made up their own factors. We know that cardiac output is a function of heart rate times stroke volume. And total peripheral resistance is a function of systemic vascular resistance, i.e. what the diameter of the blood vessels are throughout the body, and blood viscosity. Of these two, SVR tends to be much more important as a contributor to total peripheral resistance. A lot of times these two terms, because of that fact, will be used interchangeably, okay, and I tend to use SVR a lot, but in reality TPR is the more broad term, and it is determined by what systemic vascular resistance is, typically, again, vessel diameter or turbulence to blood flow and viscosity, okay? So if you take a look at this mathematical relationship, you can very clearly see if we have a situation where we increase cardiac output and TPR stays the same, mean arterial pressure goes up. If cardiac output and total peripheral resistance goes up, mean arterial pressure goes up even more. If both of these go down, mean arterial pressure will go down. In order to kind of demonstrate these relationships that I was just talking about, I wanted to take you through a particular example where we have a situation where we have falling or low blood pressure. Okay, so what we're going to have here is low BP. Okay? So here we have a cartoon picture of an artery with some specialized nerve endings, sensory nerve endings embedded in it. And the tips of those nerve endings make up a structure we refer to as baroreceptors. Baroreceptors are specialized nerve endings that get activated when the artery, the arterial wall, is stretched. We actually sometimes refer to these as stretch receptors. Okay? So as a blood vessel wall is stretched, these receptors or nerve endings are stretched as well, and that opens up mechanical ion channels that causes a depolarization in those sensory nerves and will send a signal back to the central nervous system. And that signal essentially tells the central nervous system that blood pressure is increased because of that stretch. In our particular example, we have a decrease in blood pressure, which would decrease the stretch of our arteries, which are very elastic. In that case, the frequency at which the baroreceptors fire action potentials will actually decrease. Okay? Those signals are sent, as I said before, back to the central nervous system via afferent sensory neurons, which terminate in a specific region of the brain stem, or in the medulla, called the NTS, nucleus tractus solitarius. All right. Within the NTS, we have the vasomotor regulatory center of the brain. This is the part of the brain that receives input from baroreceptors, processes that input, and then sends signals back out through efferent nerve fibers that are a part of the sympathetic nervous system and parasympathetic nervous system. So once again, we have a fall in blood pressure, a decrease in baroreceptor activity, which gets sent via sensory afferent nerves to the NTS, which will process those signals and respond appropriately in those signals by increasing sympathetic nervous system output and decreasing parasympathetic nervous system output. All right, so let's take a look at the sympathetic nervous system and what happens when it is activated. Okay, I'm going to zoom back out here a little bit because the sympathetic nervous system really impacts a number of factors here that we're going to talk about. All right, let's first take a look at cardiac output. Okay, here's a sympathetic nerve fiber releasing norepinephrine. Again, you can also activate the adrenal gland, which releases catecholamines, 80% epinephrine, 20% norepinephrine. And the sympathetic nerve fibers and the catecholamines released by the adrenal gland will activate beta receptors on cardiac tissue. Okay? Now, there are both beta 1 and beta 2 receptors on cardiac tissue. The one that we typically talk the most about with regards to regulation of cardiac output are your beta 1 receptors. So I'm going to put a little asterisk or star by those because they're the most important. Okay? As norepinephrine is released, or epinephrine from the adrenal gland, okay, beta 1 and beta 2 receptors get activated. And what that will do is that will increase heart rate, right, through stimulation of these receptors on the SA and AV node, and you'll get an increase in also stroke volume, okay, because activation of these receptors will increase contractility of cardiac muscle, and that will give you an increase in stroke volume. Sympathetic nerve fibers also innervate arteries and veins. Okay, in this case, we're going to talk about the arteries. Okay, there are alpha 1 receptors and beta 2 receptors on arteries, and stimulation of alpha 1 receptors on arteries will actually increase systemic vascular resistance and increase TPR because they cause vasoconstriction. Activation of beta 2 receptors during this circumstance can cause dilation of skeletal muscle vascular beds, but the overall effect here is an increase in TPR. Okay? The third thing the sympathetic nervous system does is that it can activate the renin-angiotensin-aldosterone system, or the RAS system. Okay, so here's another nerve fiber, and I'm just going to put beta-1 receptors here. Okay, so norepinephrine here released by sympathetic nerve fibers will stimulate beta-1 cells, okay, that are actually present in each one of the nephrons on the afferent arterial here. Okay, we have specialized smooth muscle cells here called JG cells. Okay, and they have beta-1 receptors on them, and when those beta-1 receptors get activated, what we get is a release of the peptide, the protein enzyme. Let me find a good marker here. Renin, the enzyme renin. Okay, now if you remember from our RAS video tutorial, okay, we have angiotensinogen, which is a protein released from the liver, which is a substrate for renin. Okay, and that can be converted via renin to the decapeptide angiotensin 1, and then that gets converted to angiotensin 2 in the lungs, primarily by the enzyme angiotensin converting enzyme. Okay? Now, what happens here at this point? Well, we know from our RAS lecture and our lecture on vascular resistance, or systemic vascular resistance, we have angiotensin 2 is a potent vasoconstrictor. So that can stimulate an increase in systemic vascular resistance by causing vasoconstriction through the activation of angiotensin subtype 1 receptors, the AT subtype 1. Okay. The other piece to this, if you remember from the RAS lecture, is that angiotensin 2 can stimulate release of a mineralocorticoid hormone. I forgot to put in my adrenal gland here. Okay. There are AT1 receptors here. And when they get stimulated by angiotensin 2, we get the release of a mineralocorticoid hormone called aldosterone. All right, and I'm just going to draw a dotted line over to here so I can have room to write it. We have aldosterone. Okay, now, if you remember from the RAS lecture, aldosterone can help to elevate blood pressure by stimulating sodium and water reabsorption in the nephron, specifically in the collecting duct. So we'll remember, aldosterone activates nuclear receptors in the epithelial cells of the lumen of the collecting duct and stimulate them to produce ENaC channels in sodium potassium ATPase, which allows these cells to reabsorb sodium and water. And that in turn will increase blood volume. Okay? Now we know if we increase blood volume, okay, we can increase preload. And anytime we increase preload, we can increase stroke volume and cardiac output. Okay? So again, there's a lot going on here. And when we have situations where blood pressure is high, really all you have to do is just the opposite of all of these things. And so it could be a worthwhile exercise for you to go through what you think might happen when blood pressure falls and how these factors here change. And they all just change in the opposite direction. A lot going on here, and this certainly isn't an all inclusive picture here, but rather it covers some of the major factors that regulate cardiac output, TPR, and mean arterial pressure, and puts everything together from the other video tutorials. Well, I hope this has been helpful. If you have any questions, please don't hesitate to see me or your other instructors. I wish you the very best in learning this material, and take care. Good luck.